Hello, in this video I'll be showing you another example using Feynman's techniques of integration, otherwise known as differentiation under the integral sign. So in the previous video we went over a pretty hard integral to evaluate, and we used Feynman's technique, which basically allowed us to differentiate under the integral sign and made the integral very easy. This one is another famous integral. It's a pretty hard integral to evaluate if you have never heard this technique, or you aren't really strong in your mathematics and you're only basic with your integration stuff. This would look scary. If you tried integration by parts on this, it wouldn't work. So I'm going to just get straight into the video. So Feynman's technique of integration basically means you're going to set up a new parameter. So you're going to basically make this whole integral a function of a different parameter. So the way I like to do it, I like to go f of alpha, and I'm going to replace the 5 here with the alpha. So this integral here would be f of 5. So now I'm just going to create an expression for f of alpha. So this is going to be, I'm just going to actually change the thickness of my pen so it'll be easier to write. So this would be f of 5. So f of alpha would be the integral from 0 to infinity e to the negative x squared cos of alpha x, okay? Now all we're going to do is basically differentiate with respect to alpha. So let's just make this line a bit smaller. So our next line would be f dash, if my pen works, sorry my computer's lagging, f, I'm just going to move this typing down. Boom. Alright. It would be f dash of alpha, and then we'd have the derivative with respect to alpha, and then of course our whole integral. Okay? Then be e, make that infinity sign a bit smaller, e to the negative x squared cos of alpha x dx. Alright? Now basically what we can do now is we can move this derivative onto the inside, and basically we'll make it a partial derivative. So a partial derivative is basically, instead of using a d like we use for derivative, we basically use this symbol here. Okay? So this means normal derivative, and this means partial. So what a partial derivative means is basically when you're differentiating with respect to some variable, you treat all the other letters and variables as constants. Okay? So what we can do is show f dash of x is equal to integral from 0 to infinity, and then we turn this into a partial derivative. So partial derivative with respect to alpha, e to the x negative x squared cos of alpha dx. Okay? Now if you had no idea what a partial derivative would be, you would be like, how do you differentiate that with respect to alpha? Well, x is now a constant, okay? So we just treat x as a constant now, okay? So I'm just going to rub that out and just put it back in. So we're going to differentiate this whole thing, but we're going to treat x as a constant. So our e to the negative x squared is now a constant. All we're going to differentiate is basically our cos, okay? So recall, if you differentiate just cos x, that goes to negative sine x, okay? And of course with chain rule, if it's like cos of ax and you're differentiating with respect to x, the a is going to come out the front. Okay. So in this case, our x is going to be our a. So when we rewrite this new line, we're going to have f dash of x is equal to the integral from 0 to infinity. We leave just this term here, so we're just going to have e to the negative x squared. Differentiating cos, it turns to negative sign, so we're going to have a negative here, and we're also going to have this x come out the front because x is our constant. Okay, so if we rewrite this, we're just going to have negative x e to the negative x squared sine of alpha x dx. Okay, cool. Alright, that's a lot of hard math right there. So what we're going to do now, we're going to make this a bit smaller, because now we're going to basically do integration by parts on this entire thing. Okay? So recall, integration by parts basically means if you integrate a function that can be that is differentiable a function that is integral, that can be integrated, is equal to basically uv minus the integral of v du dx. Okay? This is our formula for integration by parts, right? So we're basically going to do this with this integral right here. And we're going to treat alpha as a constant, okay? So what we do is basically we're going to choose which is going to be integrated and which is going to be differentiated. Now looking at this term here, this would be really easy to integrate just with u substitution. So we're going to let this here basically be our dv dx is going to be negative x e to the negative x squared, okay? And we're going to let our sign here be our u. So u equals sine of alpha x, okay? Now we're just going to integrate this. So recall, hold on, my computer's not loading. So recall if we just had this as an integral, and just negative e to the negative x squared dx, and we let u equal x squared up here. If you had du dx, you differentiate with respect to x, you'd have 2x, okay? Therefore, if you wanted to make this whole integral in terms of u, you could move the dx up here pretty much, and you could have du equals 2x dx, right? Okay? So, therefore, if we substitute, so if we want to make this whole thing the subject of dx. So if we have dx is equal to du over 2x. So if we substitute dx into here and u into there, we're going to turn this whole integral into basically just negative e to the u du. Okay? Integrating that stays the same, so e to the u, and of course over 2. This is going to be over 2 here. Basically, it just simplifies to e to the negative x squared over 2. Okay? So that's what's going on in there. I'm just going to rub this out now because we're going to need some more room. So that's how you integrate this part here, just by doing u substitution. Although if you're watching a video on Feynman's technique of integration, I'm pretty sure you know what u substitution is. Otherwise, you'd be very, very lost. So just integrating this, we're going to have v is equal to negative e to the x squared negative over 2. Okay? Hopefully you're all good with that. If you, actually that's going to cancel out because there's a negative, so there's no negative there. Alright? Hopefully you're good with that. If we differentiated this, we just bring the alpha outside. So we're going to have du dx is basically going to be just alpha cos alpha x. Okay? Cool. So when we rewrite this integral in terms of its parts, we're going to have negative x multiplied by e to the negative x squared sine of alpha is basically going to be equal to u, v multiplied by each other. So you can have e to the negative x squared sine of alpha x over 2, 0 to infinity, minus our new integral here, which is going to be v multiplied by du. So we're going to have e to the negative x squared alpha cos of alpha x all over 2 dx. Okay. Now let's take a closer look at this term here. Okay. So recall, we've got to substitute these bounds in for x. So if we substitute e to the negative infinity all squared sine of alpha infinity over 2 minus 0, this whole thing here, because this e has a negative exponent, that's the same as rewriting this whole thing as e to the infinity all squared down here, because of the negative exponent. So 1 over infinity, this exponential is going to increase significantly bigger than this sign, because this sign is just going to periodically go between -1 and 1 as it goes to infinity. But this number here, as it goes to infinity, is going to get bigger and bigger. So if you have 1 over a really big number that's just going to keep getting bigger, you basically have 0. So what that means is this whole bracket term here in the by parts, this whole thing here is equal to 0. So we're going to rewrite our line now. It's basically just the integral of 0 to infinity, negative x e to the negative x squared, sine of alpha x dx is equal to negative e to the negative x squared alpha cos of alpha x over 2 dx. And then, of course, you have 0 to infinity here. I forgot the bounds. Alright, this, basically what we're going to do now to solve this is we're basically going to turn this into a differential equation. Because recall, this here, this whole thing here, is f dash of alpha. Okay? And if you look in here, you can take out a factor of negative alpha over 2, right? And then you're just left with this integral here, 0 to infinity, e to negative x squared cos of alpha x over 2. Oh, the 2's gone. Isn't this just our normal integral that we have up here? That we defined as f of alpha? So therefore we can substitute this whole thing here for just f of alpha. F of alpha. And let's just go to the next page. So we have, basically we're saying is the derivative of f with respect to alpha is equal to negative alpha over 2 multiplied by f. This is a separable differential equation pretty much. I'm not going to write it because the computer's lagging. Alright? Now the way we do this is basically we get all our f's on the side with the df and all of our alpha on the side with the d alpha. So all we're going to do is move the alpha up here and move the f down there. So we're going to divide by f and divide by f on both sides and multiply both sides by d alpha. So we're going to left with df over f is equal to negative alpha over 2 d alpha. And basically all we got to do now is integrate both sides. So chuck an integral on. The left hand side is going to be the natural log of f plus a constant. It's going to be negative, this side is going to be negative alpha squared over 4 plus a constant because of the power rule. Then we're going to move our constants to the the right hand side. So we're going to have natural log of f is equal to negative alpha all squared divided by 4 plus some constant, because this has got constant 1, this constant 2, and this constant here could just be constant is going to be c2 minus c1. Okay, that's all that is. Alright, there's another thing we can do here. We're going to make f the subject, so we're going to change a base. So we're going to have f is equal to e to the negative alpha over alpha squared over 4 plus c. What we can do is change how this looks pretty much. Recall our index laws. If you have am multiplied by a to the n, that's equivalent to am plus n, a to the m plus n. That's the same go with this. So we can rewrite this whole thing as f is equal to e to the c multiplied by e to the negative alpha squared over 4. We can say this e to the c is just some constant a. So therefore we can rewrite this whole thing as f is equal to a e to negative alpha squared over 4. Wow, this is a tough integral. You've been using separation of variables and all sorts of crazy. You've also done some limits in this. So this is a really good integral to get under your belt and understand, right? So basically this whole thing here now, we basically say we've got an expression for the evaluation of this integral. Basically 0 to infinity e to the negative x squared cos of alpha x dx is equal to some constant multiplied by e to the negative alpha squared over 4. Now how are we going to find this a? Well, I'll tell you what we're going to do. We're going to let alpha equal to 0. The reason we do that is because this term will go to 1. And this whole term in front of that, it will just get a by itself. So we're going to have 0 to infinity e to negative x squared cos of alpha times 0 is just 1, so that's going to be dx, is equal to a e to the 0 or squared over 4. This whole thing is going to be turned into 1, so we just have this expression for a. Now recall, this is the Gaussian integral. Now this Gaussian integral is actually equal to the square root of pi over 2. I'll be covering that in a later video. Okay? So basically a is equal to the square root of pi over 2. Therefore, we can say the integral from 0 to infinity e to negative x squared cos of alpha x dx is equal to the square root of pi over 2 e to negative alpha squared over 4. Now our original integral was, instead of having alpha, we had a 5, okay? So all we're going to do to basically evaluate our integral is replace the alpha with a 5. So we have 5 squared over 4. So therefore this whole thing is square root of pi over 2 e to negative 25 over 4. And that is our integral solved. Now this was a tricky integral to do. But if you learn how to do this one, it will get your mathematics so much better because you're using Feynman's technique of integration. You're also using integration by parts. You're also evaluating limits here, and you're also doing separation of variables via differential equations. So this is a really good integral to this is a really good one to learn.